For months, the conversation around 3I Atlas followed a familiar path. A fast-moving interstellar object enters our solar system. Telescopes lock on. Early data is noisy. The safest assumption is repeated. It's probably just another comet. Unusual, yes, but still explainable. That narrative held together until a single graph quietly circulated among researchers. No dramatic press release, no headline announcement, just a curve on a plot that refused to behave. That graph didn't just challenge one theory. It undermined nearly all of them. At first glance, the graph looks ordinary. Time on the x-axis, brightness on the y-axis. Hundreds of objects have been plotted this way before. Comets brighten as they approach the sun. Asteroids stay relatively flat. Interstellar visitors usually follow predictable thermal and reflective patterns. The problem is that 3I Atlas doesn't follow any of those lines. It diverges sharply, bending away from every known category like it's obeying a different rule book. What makes this graph so disruptive is not a single spike or anomaly, but the shape of the curve itself. As 3I Atlas approached the inner solar system, its brightness increased, but not smoothly. Instead of the gradual exponential rise expected from sublimating ice, the graph shows abrupt plateaus followed by sudden jumps. Then, just as abruptly, it stabilizes again. No dust cloud expansion, no correlated gas signatures, just light behaving badly. For comet scientists, this is a nightmare scenario. Comets are messy, but they're consistent. As solar radiation heats the surface, volatile ices vaporize, dragging dust outward and increasing reflectivity. The brightness curve should mirror distance to the sun. With 3I Atlas, the brightness increases even when solar input remains nearly constant. In some intervals, the object brightens while moving away from peak heating conditions. That alone should not happen. Early attempts to dismiss the data focused on instrumentation error. Perhaps the angle was wrong. Perhaps background stars contaminated the readings. But the same pattern appears across independent observatories, using different instruments at different wavelengths. Optical telescopes saw it. Infrared sensors confirmed it. Even radar returns hinted at something unusual in surface response. When errors line up this cleanly across systems, they stop being errors. The next explanation was rotation. Maybe 3I Atlas is tumbling, exposing reflective surfaces intermittently. But the graph doesn't show periodic oscillations. There's no repeating rhythm. The changes aren't cyclical, they're step-like. Rotation would create a wave. This graph looks more like a staircase. That's when a few researchers began overlaying comparison curves, not just from comets or asteroids, but from artificial objects, space debris, defunct satellites, solar sails. The goal wasn't to imply anything exotic, but to rule things out. Ironically, that comparison only made things worse. Artificial objects show sharp brightness changes, yes, but they also show specular reflections and polarization signatures that 3I Atlas lacks. It behaves unlike natural objects, yet also unlike engineered ones. Another strange feature emerges when you look at slope changes. The brightness jumps occur at thresholds, not continuously. Almost as if something activates once a specific condition is met. Temperature, radiation level, or even local plasma density. In physical systems, threshold behavior usually implies phase changes or control mechanisms. Ice doesn't do that cleanly. Rock doesn't do it at all. One particularly unsettling detail is what doesn't accompany these brightness shifts. There's no corresponding increase in outgassing, no detectable coma expansion, no tail growth proportional to the light curve. The object gets brighter without throwing material into space. That violates the most basic cometary physics. Light, in this case, is decoupled from mass loss. Some have suggested exotic surface chemistry, perhaps a crust of volatile compounds that transition states rapidly. But even the most speculative materials proposed in astrophysics don't produce the clean, repeatable steps seen in the graph. Nature tends to smear things out. This graph is crisp. Then there's the thermal angle. When scientists plotted temperature estimates alongside brightness, the mismatch became impossible to ignore. In several intervals, the brightness rises, while surface temperature remains flat or even declines slightly. That means the increased light isn't coming from heat-driven emission. it's reflectivity, or something masquerading as it. At this point, the phrase passive object starts to feel inadequate. Passive bodies respond smoothly to environmental forces. 3i Atlas responds selectively. Even more troubling is how the graph evolves over time. The first brightness jump occurs far earlier than expected, well outside the region where solar heating should matter. The second occurs closer in. The third doesn't align with any obvious external trigger at all. If this were purely physics, the triggers would be monotonic. They're not. Some researchers have tried reframing the graph statistically, arguing that we're seeing a rare but natural outlier. That defense collapses when you realize how many independent assumptions it requires. You have to assume unusual composition, unusual structure, unusual rotation, unusual surface chemistry, and unusual interaction with solar radiation, all at once. Each assumption is unlikely. Combined, they're vanishingly so. What makes this one graph so powerful is that it compresses all those improbabilities into a single visual. You don't need a complex model to see the problem. The line simply doesn't belong. Historically, graphs like this are inflection points. The Hertzsprung-Russell diagram reshaped stellar evolution. The galaxy rotation curves exposed dark matter. In both cases, the data didn't scream its conclusion. It quietly refused to fit. That's exactly what's happening here. Importantly, this graph does not prove that 3i Atlas is artificial, intelligent, or anything else sensational, but it does prove that the default explanation, just another comet, is no longer defensible. The object violates too many independent expectations simultaneously. At minimum, it represents a class of interstellar bodies we've never encountered before. There's also a sociological element at play. Scientists are trained to distrust extraordinary claims, but they're also trained to follow data. Right now, those instincts are colliding. The graph is forcing a recalibration, not toward a specific answer, but away from complacency. What happens next is telling. Rather than converging on a new model, researchers are fragmenting into camps. Some focus on exotic materials, others on plasma interactions. A few are revisiting assumptions about interstellar formation environments. That's usually a sign that something genuinely new has appeared. And it all traces back to that graph. As more data comes in, the curve may change. Additional points could smooth it out or make it even stranger. But the damage to the old narrative is already done. Once you've seen a line that breaks every rule you expected, you can't unsee it. 3i Atlas entered our solar system as an anonymous visitor. It stayed quiet. It didn't flare dramatically or threaten Earth. Instead, it did something far more disruptive. It produced a simple graph that refuses to behave. And sometimes that's how revolutions in science begin, not with explosions or announcements, but with a line on a chart that quietly says, "You don't understand this yet."